Okay, so now we have the second speaker, Professor Lin Yang. So Lin Yang right now is an assistant professor at University of California, Los Angeles. And his research focuses on developing and apply fast algorithms for machine learning and data science. His current research focuses on reinforcement learning theory and applications, and also learning from control and non-convex optimization. So he has published many papers and served as area chairs for top machine learning conferences such as SML, NeurIPS, and ICLR. He was a recipient of the Simons Research Fellowship and Dean Robert Roy Fellowship and the Johns Hopkins Minds Best Dissertation Award. So today he's going to talk about something about reinforcement learning theory. So let's welcome Professor Yang.
All right, thank you so much for the introduction and the invitation, and it's my great pleasure to speak here. So today I'm going to talk about our newest result about settling the horizon dependence of sample complexity in reinforcement learning. So this work is joint work with Rosen Wang and Yuan Li. Okay, it has been accepted by Fox this year. Okay, it's going to be appeared there. All right, let's start. So actually, this talk is about reinforcement learning, and perhaps many of you have already been familiar with what is reinforcement learning. So let me just briefly mention what's the model. Okay. So in fact, here we're gonna have an agent. Okay, so the agent wants to learn how to interact with the unknown environment. So and the agent, it's actually a decision-making problem, sequential decision-making problem. So the agent wants to take a sequence of actions, for instance, from A1 to AH, and then use those actions to interact with this unknown environment. And then once an action is taken, the agent is receiving feedbacks. There are two kinds of feedbacks. One is the state feedback, and the other is the reward feedback. Okay. The state feedback represents the current status of the environment, and the reward feedback is simply a scalar. Okay, so after a sequence of actions, then the environment is returned back a sequence of state feedback and reward feedback. Okay, and the goal of the agent is to maximize the so-called long-term cumulative rewards. That is, expected sum of all the rewards. Okay, so as you can see here, this we can see the sequence of rewards of length h. Okay. So the length of this sequence is called the horizon of this problem. Okay. So compared to other machine learning paradigms, this perhaps is the most distinct difference between this reinforcement learning and other types of machine learning paradigms is the dependence of h. Okay. All right. So more formally, so reinforcement learning, this underlying model is the so-called Markov decision process model. Okay. Here, the environment is represented by a finite state machine. Okay. So in this machine, there are finite set of states will be represented as S. For instance, in this picture, we have 3 states. And in each state, you can interact with the environment with actions from certain set, actions A. Okay. For instance, at this picture, at this state at 0, you can interact with it with action A0 or A1. Okay. Once you take an action here, the environment is going to perform state transitions, okay, based on certain probability that is fixed but is unknown to you. Okay. For instance, here you play this action, you're going to transition back to itself with probability a half, or transition to another state with probability a half. Okay. And at the same time, you're going to receive a reward feedback. So which reward here, which will usually normalize that to be a number bounded by 1 and 0. It's between 0 and 1. Okay. It can also be other ranges. We just usually take that as for convenience. Okay, take this region for convenience. And then the horizon is represented by h again, right? So now, given this kind of setting, we are interested in finding a policy. So the policy here is simply a function that maps a state and a step, right? So you have the length of the horizon is h, right? So at each step, and if at a state s, right? So this policy maps these two things to a distribution on the action set. Okay. It tells you how to plan an action. Of course, here we can see the more general setting that you're going to take a random action from a certain distribution. Right? If you do so, you can receive a sequence of random rewards, right? And to take the expectation of this random rewards, that gives you the so-called value function, which we're really interested to maximize. Right? The optimal policy is the policy that maximizes this value function. Okay? Of course, because the probability is unknown, right? So we usually want to get some suboptimal policy, for instance, epsilon optimal policy, since getting the exactly optimal policy might not be possible statistically. Okay? So we're interested in getting a policy that is epsilon optimal compared to the optimal policy. Okay? So of course we're considering this PEC complexity, an algorithm that is probabilistically correct, right? So for instance, it is correct with probability 0.9, and we still wanted that algorithm to output a policy at least epsilon correct, right? It's epsilon optimal, correct? So in this kind of problem, there are already a lot of results. So all of them probably share a very similar structure that is depicted in this picture. For instance, in the beginning, right, so you know nothing about the environment, you usually start with the arbitrary policy and use that to interact with the environment and collect a bunch of data points. So once you collect the data points, you can use these data points to improve and to get a new policy and to collect more data. So basically, you start with some policy and you interact with the environment by taking a sequence of actions, right? That is called an episode of interaction, right? And then once after this episode of interaction, you get an episode of data, right? Use this data, you get a new policy. You just continue this iteration again and again, and your expectation is that your algorithm becomes better and better. You collect more and more data, right? Okay. So using this kind of framework, there are a lot of results. They're already achieving the PEC bounds. So of course, these results in those papers are not represented by PEC bounds. So I'm just rewriting their bounds as a PEC bounds. Okay. So as you can see here, all this result has a dependence on the horizon, is polynomial depending on the horizon, and linearly depending on the number of states and actions. Of course, because this distinct difference between reinforcement learning and other machine learning paradigms, right, is because of this horizon dependence, it's really important to understand the horizon dependence correctly. Okay. Because here they have been showing that under this condition that reward bounded in 0 and 1, the corrected dependence might be h to the cube. Okay. However, that might not be a fair setting. Okay? That might not be a fair setting to compare the horizon because it might purely due to the scaling factor of the reward. For instance, if you consider reward bounded in between 0 and 1, and for different horizon, let's see, then the value function is different. The magnitude of the value function is different. So for h equal to 1, right? So your value function can be at most 1, and for value 100, so for h equal to 100, your value function can be at most 100. So the scaling factor gives the so-called noise to understand the dependence of horizon. So probably we should consider a more fair setting. Okay? So that is the so-called bounded total reward setting, where we consider this using the same MDP, but the reward we use a different boundedness condition over it. That is, the reward is assumed to be satisfied by the following condition. That is, you take a sum of all the rewards for any trajectory. It is upper bounded by 1 almost surely. And of course, we have been assuming that the reward is lower bounded by 0. Okay, so this is a so-called bounded total condition. It looks like just a scaling compared to the previous thing, right? Of course, this is actually more general. So the previous reward bounded between 0 and 1 condition is known as the reward uniformity condition. Okay, so actually, if you want to convert that to this setting, right? So you need to rescale all the rewards by a factor of 1 over h. So in that regard, right, all the rewards becomes in between 0 and 1 over h. And of course, for all the previous results, the leading term will have no dependence, will almost have no dependence on h. However, all those results are depending, they have a second lower order term depending on h either polynomially or polylog, okay, at the best. Okay, that's the situation. Okay, so now with this more fair setup, right? So what is exactly the horizon dependence on the sample complexity of reinforcement learning in terms of this horizon dependence? So that's the core question in this talk. All right. So let's see. For this particular question, there are already a bunch of previous results. For instance, let me just re-describe the problem, right? So we want to have a pack bond. Basically, we allow our algorithm to interact with the environment for n episodes, and afterwards, we want to have a O1 opt-in policy with high probability. So to get rid of all other noise, let's consider we have just constant number of states and actions. Okay. Remember, the state and actions are just constant. All right. So then, what is the dependence on edge merely, right? So this problem actually coming up from a code open problem by John and Agal. In this code open problem, they just ask what is the correct dependence of edge, right? So they're actually conjecturing that there might be a omega edge lower bound. Basically, it's a polynomial lower bound. Like no matter what algorithm you're using, you have to interact with the environment for at least omega edge episodes. Okay, so here the complexity is measured by the episodes, not the total number of samples. That is a slight subtlety. Okay. And then in 2020, and so me and Kahardi, so we actually have a result that refutes this conjecture. Basically, we have a result saying that, okay, you can actually use only polylog edge samples to interact. I mean, the samples here is episodes again, okay? Interact with the environment, and then you can get a good policy already instead of using polynomial in edge mining episodes. That's actually surprising, right? And due to we already have a lot of new techniques in that paper, so we're actually conjecturing that maybe omega polylog edge is the lower bound. And then then after that, there are a lot of works and let's see, improving this result, because in this paper the time complexity is not that good. So there are a bunch of other papers following up this paper, basically improving either the statistical complexity or the computation complexity, but all of them has the same problem, that is they are depending on edge, at least polylog, okay? Polylog arithmetic, okay? All right, so what's new here? So in this talk, this paper is going to be appear in Fox 2020. We basically show that if you want to have a good policy with high probability, then O1 episodes interaction is already suffices. Okay, that's kind of surprising, right? It's tight in edge, and it tells you that there's no dependence on edge if you just consider this episode complexity. Right. So I say something else, right? It says that, okay, no matter how long the horizon is, the long horizon problem, short horizon problem, they kind of have the same complexity. Of course, here there's a subtlety here. Like I said, right, we're considering episode complexity. For long horizon, right, so one episode contains more samples. That's the subtlety. And also that's why you can get this no dependence on horizon. All right, so of course this result still has a drawback because it has a dependence on certain action pairs exponentially, but this is a first step to understand the exact dependence of the sample complexity in terms of the horizon, right? All right, so this again refutes the conjecture of our own paper. All right, so we don't have this omega polylog edge lower bound, right? So we have O1 upper bound. Okay. All right, so if everything's clear, let me just take several slides to introduce our techniques. Of course, I won't have that much time to go to too much details. All right. So to introduce the techniques, let me just start with this polylog edge algorithm that we introduced in 2020. Okay. So actually, to solve this problem, the most natural algorithm you can think of, it should be the dynamic programming thing, because reinforcement learning is a stochastic decision-making problem, right? You can solve it using dynamic programming, and if you don't have the exact model, you can solve it by collecting samples and solve it approximately, yeah, using approximate dynamic programming. However, if you do so, you need to do that very carefully in order to get a good horizon dependence. If you don't do that carefully, you probably will be suffering from a polynomial edge bond. Okay? If you do that very carefully, for instance, by the paper by Simon Zhang et al., okay, so they can have a polylog edge dependence using this total boundedness condition. Okay? But it's actually like if you no matter what you do, okay, so this polylog edge factor is always there. So again, it's then conjecturing that maybe if you use dynamic programming type method, okay, so this polylog edge bond is real, right? So you will always suffer from such kind of bond because you are using dynamic programming, because there are a lot of subtlety in terms of dependence issue, etc., in using a dynamic programming based algorithm. Okay. So what we do in this paper, DWYK 2020, is using a new idea that's merely from Monte Carlo estimation instead of using dynamic programming. So basically, we just want to have an algorithm that can using Monte Carlo method to estimate a value function of a policy. Okay. So this idea comes from the following observation. Basically, for a given policy, if you want to estimate the value function of the policy up to, let's say, 01 accuracy, the number of episodes to do so is only 01, because for each episode, right, if you collect an episode of data, you're gonna get a estimator which is unbiased for this value function of this policy, and the variance of that guy is order 1, right? So since the variance of this random variable is already 01, to estimate up to 01 accuracy, you only need 01 samples. That's the idea. Of course, if just doing so, right, so then there are so many policies out there, right? So you want to estimate the value of every policy in order to find the correct and the optimal, near optimal policy. Then you're going to suffer exponentially in terms of the horizon, which is not good. So the second idea is the so-called sample reuse. We basically reuse the samples of the estimator for other policies. Okay? So this sample reuse tells us that we can actually estimate a lot of policies. Okay? For instance, if you can estimate n policies, we can actually use only polylog n samples to do so. Okay? That's the second core idea. And the third core idea is that it's still not enough yet, right? So for instance, the polylog n samples here, if we want to estimate every policy, we don't care about the dependence of FSA again, okay? For every policy, then we're gonna suffer, and we're plugging in something like exponential in the horizon, we're gonna suffer from a poly edge bond, right? That's not good. The third idea in the paper is that we have a better candidate set for policies. So that's what we call the policy cover. Basically, we come up with a set of policies. If you find the best policy in the set, then that is guaranteed to give you a good policy. Okay? So this set happens to have the complexity depending on h like this form, h to the SA. Okay. So now you plug in this thing into this bond, right? You immediately get this polylog edge bond. All right, SA polylog edge. Okay. But this is the best we can do. It seems like polylog edge using the previous technique is unavoidable. Okay. Okay, so now what's new here? So so if you look at the previous result, right? So the core and one of the main contribution of my edge count dependence is from the policy cover, right? Of course, there are other dependence, which I ignore, but here I just want to tell you that the most important contribution of edge dependence is coming from the policy cover, the size of the policy cover. Okay? And the size of the policy cover is polynomial in edge, right? You take a log of that, you get a polylog edge, which is not okay. All right. So maybe we can do better, right? So one of the policies that we can use is the so-called stationary policy. So all the previous policies that we consider, like in the third slide where I'm introducing, the policies is depending on the time. Okay, so that's the so-called non-stationary policy. And the non-stationary policy automatically have a complexity dependence on the horizon. And maybe we should consider another set of policies. That's the so-called stationary policy. The stationary policy basically has no dependence on the time. It basically maps each state to a distribution of actions or to an action. Okay? If you consider such kind of stationary policies, then you don't have that many stationary deterministic policies. For instance, for S states, each state has A actions, right? The number of such policies is at most A to the S. Has no dependence on H. That is a good thing. Okay? Well, but it has some problems because we know that in such a finite horizon problem, if you use stationary policy, then you are not guaranteed to get an optimum policy. Basically, it means that optimum policy usually has to be the non-stationary one. Okay, so that's the problem. However, in infinite horizon problem, so stationary policy is usually okay, and it is usually giving you the optimum policy. So that's kind of a very interesting thing, right? So for finite horizon, you have to use non-stationary policy. But when you make the horizon goes to infinity, and then it suddenly tells you that you can only use stationary policy, which is a very intriguing thing to think of, right? All right, so maybe we can just use this set of policies as the candidate policy cover. Of course, we are not guaranteed to get the optimum policy, but we can use it differently. So the idea is that use this set of policy maybe just to collect the samples, okay? And then use the collected samples to solve for instance, the optimum policy, right? So that's actually the kind of the idea. So basically, we are using this all the stationary policies to collect the data, and that will give us an empirical Markov decision process, and then we solve for a good policy from this empirical Markov decision process. However, like I said, right, so this set of policies is not guaranteed to be optimal. It does not guarantee to contain the optimal policy in terms of the entire problem. So the sample collected might not be good enough. And on the other hand is that the number of samples collected, if we're using previous technique, it usually requires a lot of samples. Usually require the collected samples to be depending at least polynomially in the horizon, which is a big problem. To address this problem, we come up with the second idea, that is the so-called perturbation lemma. So what this perturbation lemma says is as follows. Basically, you can see the probability transition matrix, which I depicted here, PSA transition to S prime, right? This is a probability. So if you have an empirical probability matrix estimated to this guy, has error dependence something like square root 1 over h. Okay, so this is actually possible because if you collect a single trajectory of data, it contains h samples, right? Ideally, if all the samples are independent, and then you can get such kind of error bond, right? So of course, I'm just I'm just presenting here to ideally, and in the paper, there's a lot of subtlety and ignoring. Okay? So this is actually what we can get. Okay? So that is square root 1 over h bond is what we can get for estimating the error, for the estimating error of the probability matrix. Okay? So then, our perturbation bond says, and that, okay, it's actually enough. Okay, so if you just have this kind of approach and the error on your estimator, then you can have a O1 optimum policy out format. Okay, so this would not be true using previous technique. For instance, if you're using dynamic programming based method, you have such an error bond, right? So then the final error bond is this guy times horizon. Okay? That basically tells you that if you use the previous bond, then you're going to be suffering with a square root error overall, which is very bad, right? So this new perturbation lemma says that the previous bond are really loosey, right? So basically for this guy, you can have a one optimum policy. That's the first major idea to achieve this no dependence in horizon. Okay? And the second core idea is to establish the approximation ratio between stationary policy and non-stationary policy. Like I said before, right? So if you only consider this set of non-stationary policies, it's not guaranteed to contain the optimum policy, I mean, in terms of this finite horizon problem. However, we can actually establish a approximation ratio between this stationary policy and non-stationary policies. So this is via the using this discounted infinite horizon Markov decision process as a proxy, and eventually show that if you consider discount factor, which there's a lot of subtlety here, I'm going to ignore, you can just understand that if we use this stationary policy in the finite horizon problem, you're going to get a multiplicative approximation of the value of some policy in the non-stationary policy in the original problem. And then this multiplicative approximation factor is actually only depending on the number of states, which I depict here, fs and gs. They're pure functions, okay? So as you can see here, the dependence is only on the states, not on the horizon, right? So that's a kind of interesting thing, right? You can approximate the value of a non-stationary policy using stationary policy with the approximation factor, no dependence on the horizon, which is kind of surprising. So with this kind of thing, we can actually use this set of policies to collect the samples and then use that to achieve so our previous perturbation lemma. Okay, and with these things, we can actually eventually have this bond. Okay. All right, so there are actually a lot of other subtleties. For instance, what I'm describing to you is about to estimate the expectation, okay, or the mean of a certain estimator. But we want to have a high probability estimation, especially in this online setting when you're collecting a sequence of samples. This mean is actually not good if you look at a paper. Okay, so it doesn't mean that you have a good mean. Doesn't mean that you have a high probability bound. Basically, we use another thing to let's say mediate this kind of thing, that is quantile. So eventually, all our bounds is used is proved using the quantile, but our technique is only for mean. So we have to establish a connection between the mean and the quantile. Okay, so that's actually another interesting thing. And finally, the final data collection policy has another subtlety. For instance, we are not using exactly the set of stationary policies. We actually concatenate two stationary policies. Okay? So use one stationary policy to reach certain state, and then from there, you play another stationary policy. Of course, this kind of policy, right, to concatenating two stationary policies, does not introduce too much complexity, because the overall complexity of such policy set has still no dependence on the horizon. Okay? As you can see, the number of such policies is this guy. Of course, it's exponential in S. All right, so the final step is to use a so-called pessimistic planning to mitigate some kind of estimation error in certain trajectories. All right, so these are all of these techniques that it's my best to describe to you in just 20 minutes. Okay? So overall, let me give you a summary. So what we have is that we show that under this total bounded reward condition, which is sum of the rewards is less than 1 almost surely, then if you want to get the O1 optimum policy, then the number of samples to do so has no dependence on the horizon. Okay, so it's O1 dependence. Okay, O1 number of episodes. I'm sorry. Okay, so there are a lot of technical results we're coming up with. To get this result, they might way of independent interests. For instance, the perturbation lemma or the approximation lemma. On the other hand, the approximation lemma says that actually you can use this stationary policy to achieve good for this finite horizon problem, which somehow explains something in practice, because in practice people always consider discounted stationary policy rather than non-stationary policy for whatever problem, right? This kind of approximation lemma somehow explains such a kind of phenomena, right? All right, so there are certain open questions left from this result. In particular, we don't have a good dependence on the state and actions. So it might be good to have a good algorithm to achieve tight dependence on horizon and also tight dependence on state and actions. Okay. So that's everything of my talk. Thank you. Yeah, I'm here to take questions there.
So very nice talk. Thank you, Lin. So I have one question. So do you believe that the optimal dependence on SA is a polynomial or exponential?
So I do believe it's a polynomial, because if you allow a polylog dependence on H, then you already have algorithms that is polynomial depending on S and A. Yeah. In particular, Simon and their new result is also time efficient.
I see.
Yeah.
Okay. So also, can you say just a little bit more words on the perturbation lemma? So why so you don't need the dependency on H?
Yeah, so actually it's coming from this, I think it relates to this KL divergent stuff. So basically, how to say about that? Yeah, so basically, if you, like, the best worst case bound is one with square root H, right? But if that is because you're only considering a single, like, a pointwise approximation. But if you treat the whole vector as a probability vector, the overall approximation is actually much better. If you use the naive one, you just take a sum of all this square root H thing, that is very bad. But if you consider a vector as a whole, then the overall one is coming from the KL divergence, etc. That can be much better. Basically, what we have here in terms of perturbation is computing this thing as a whole thing rather than a pointwise approximation.
Okay.
Yeah.
Okay. I will look at the paper. See. Okay. Any question? Other questions from this room?
Could I also ask a question about
Sure.
this talk?
Yeah.
Actually, I might miss a point in the very beginning setup. I just wondering, so for this O1 dependence result, is it on the stationary MDP or non-stationary MDP? That is like for
non-stationary MDP.
Non-stationary. So you allow like the transition to be different at different steps.
I'm sorry. So I got it wrong. So the probability transition needs to be stationary.
So it's the same for every steps for both transition and the rewards.
Exactly. Otherwise, I don't think it's possible to get to O1 dependence. That's
also, thanks. And also another question is like, I know it's not covered in this talk, but I just wondering about your opinion. Like, how would you feel? Is it possible like the actual minimax rate is something O1 in H, but exponential in H, like something like minimum of exponential in SA, or like comma polynomial H times polynomial SA, something like that? Is it possible something of this happening?
That seems crazy, but it might be plausible, because right. So right now, all techniques gives us either exponential in SA and or polylog in H, right? So maybe that's the minimum of the two. I'm not sure. That's a good point. Yeah.
Okay.
Yeah.
Cool. Thanks.
Okay. So any other question? So if there's no further question, thanks again.
Thanks.